So now that we've had a chance to find out about the numbering systems and binary values and hexadecimal values, you're probably saying to yourselves, that was a lot of fun, but what does it have to do with this chapter? This chapter is actually called Data Representation, and the whole point is to get an understanding of how data is represented in our computers. So ordinary people thinking up brilliant stuff said to themselves, how can I represent data in a computer that only understands binary, ones and zeros, yes or no, true or false, the presence or the absence of electricity? So they said, how many characters do I actually need to represent? If I have uppercase letters and lowercase letters and some numbers, and we'll throw in periods and exclamation points and other symbols like that, they decided that the most that we would ever need to represent in the English language was 128 characters. And so how many bits would I need in order to be able to uniquely represent 128 different characters? And they decided that I would only need 7 bits. Because with 7 binary bits, I could uniquely represent 128 unique bit patterns. So let's say, for instance, with 7 bits, 1, 2, 3, 4, 5, 6, 7, let's say that this unique bit pattern represents a capital letter A, and let's say if I just change one thing about it, or 2, that's going to represent a lowercase b, and then maybe I want a capital Z, so I'm going to say that this is equivalent to a capital Z. So an organization called Ascii, which stands for the American National Standards Institute, wanted to be able to standardize all of these bit patterns. And so Ascii created a code called ASCII, A-S-C-I-I, which stands for the American Standard Code for Information Interchange. And the whole point was to standardize these bit patterns, 7-bit patterns, to represent, say, the capital letter A or the lowercase a. It gives us 128 characters in the English language to represent. The only problem is 128 turned out not to be enough, and so they actually decided to increase it by 1 bit. So with 2 to the 8th bit, we could have 256 different characters. We're going to call it extended ASCII. So do I have to get rid of all of the original 128? Actually, no. The only thing that I have to do is add a new bit to the beginning, a leading 0. I can keep all the original 7, and then when I add something new to the front, put a 1 in the front, now maybe I'm going to have a question mark. Or the extended ASCII allowed us to double the number of symbols that we could represent in the English language. So if you're curious to know what these first 128 characters are, turn in your book to page 595, and there is the 7-bit ASCII table that you can see. Now, when I look in that table, I'm going to actually see that a capital letter A is a decimal 65, and that bit pattern, I was kind of making up those bit patterns before, but that pattern is 1000001. That is the actual bit pattern for a capital letter A. It is a decimal 65, and we know how to convert decimals into binary. So a lowercase a is actually a decimal 97, and that value is going to be 01100001. And just for the last one, we will do the capital letter Z is the decimal value 90, and that represents a 01011010. So these are the actual bit patterns for each one of those individual characters. So I said that when we extended ASCII, now we can represent 256 different characters in the English language. What is the problem with that statement? The problem is the English language. As computing went global, we needed to be able to represent more than just characters in the English language. So ordinary people thinking up brilliant stuff came up with this idea of Unicode. And Unicode expanded on the 8 bits in the extended ASCII, and they actually are using 16 binary bits. And with that, I can represent over 65,536 different unique bit patterns. So I can represent over 65,000 unique symbols in, I'm not going to say the entire human language, because Unicode does not cover all of the written human languages, but there are quite a few of them in there. So that begs the question, do I have to get rid of the original 256? No, all I have to do is expand them out. I'm going to put leading zeros on all of these 16 bits, and now I can use the original 256, and now I have 16 full bits that are available to me. And so Unicode characters are generally represented in hexadecimal instead of in decimal or in binary, mainly because with 16 bits, that's only 4 hexadecimal characters. And so 3095 in hexadecimal is actually the symbol that looks something like this. And the binary, the 16-bit binary bit pattern would look something like this. Okay, so that's letters and numbers and symbols like exclamation points and whatever exactly it is that this hexadecimal Unicode symbol looks like. But how do I represent other data in my system? The next thing that we're going to talk about is color. How do we represent color? Well, we're going to find out that color, this same principle applies for colors as it did for letters and numbers and symbols. We need to be able to represent different colors, all of the colors in a Crayola box. As a matter of fact, the human eye can distinguish over 16 million different shades of color. That means that I'm going to have a bit pattern for off-white and eggshell white and fluffy bunny white and burnt sienna white, and just go into Home Depot. It's remarkable the number of shades of any given color you can find. Generally, we represent colors in terms of 24 or 32-bit color. That would be 2 raised to the power of 24 or 2 raised to the power of 32. If I'm using 32-bit color, which is pretty common, that means there are 4 bytes for every color. 4 bytes are 32 bits. Remember, a byte. 1 byte is equivalent to 8 bits. So if I have 32 of them, that means I actually have 4 bytes. So let's see about color. If I want to paste an image onto my screen, let's say that you have a screen, this one is kind of slanted off to the side, that has a resolution of, we'll say that it's a 1024 by 768 resolution monitor. That means that there are 1024 pixels side to side, and that means that there are 768 pixels from top to bottom. That means that there are 786,432 pixels on a screen that has this short resolution. I'm just going to round that up to 800,000 pixels on that screen. And so if I want to represent color on this particular screen, I'm going to paste an image or put an image on this particular monitor. That means each one of the 800,000 pixels on the screen is going to need to have a unique color. So if I'm using 32-bit colors, I have 800,000 pixels on the screen, and each one of them requires 4 bytes. Each pixel, let's say for instance that you're going to put a picture of Shrek up there as he's talking to Donkey. So each one of those pixels is going to either be a green or a light green or an off green, maybe the brown from the tree behind him, maybe the brown of Donkey. So with 800,000 pixels, each of them requiring 32 bits worth of color, that means that I am going to need 3.2 million bits just to represent a single image on a monitor with a 1024 by 768 resolution. 3.2 million bytes. That means the file size of 3.2 megabytes, right? Or a 3.2 meg file. So color is represented in the same method as letters and symbols are. So what if I wanted to expand this out to video? Because now I don't just want a picture of Shrek as he's talking to Donkey. Now we want video. So I have the same resolution monitor. This time I have a refresh rate. So let's say for instance that I am refreshing my screen at 30 frames per second. That means 30 times per second. each one of those 800,000 pixels are being refreshed with perhaps a new color. Let's say, for instance, Shrek is moving across the screen as he reaches down to hand Donkey something. And so just one of those 800,000 pixels might go from green to lighter green, and maybe flashing to the brown of the tree behind it as Shrek moves out of that frame. Which means now I have a 3.2 meg file that is refreshing at 30 frames per second. And this has now taken my file up to 96 meg in size. And that's just for 1 second of video. So how do we represent sound? Because Donkey and Shrek are most definitely making some sound. We represent sound in the exact same way that we represent the others, with bit patterns. Sound is generally represented with 16 bits, and with 16 binary bits, I can represent over 65,000 unique combinations. So my apologies for anybody who is listening to this, but there might be a bit pattern that represents a sound way up here, and there would be another bit pattern to represent a sound way down here. Over 65,000 different unique sounds that I can combine with the color and the data with the numbers and the symbols in order to represent data in a computer. So what happens is those bit patterns are being fed one by one into the processor. And so if maybe the instructions are coming into the CPU or the processor from the keyboard, maybe the instructions are coming in, the next 16 bits are going to be a character, and so it'll read in them one bit at a time, all 16 bits, and it will paint a capital letter A on your keyboard, on your Word document, and then the next 16 bits might be a capital letter Z, and then the next 16 bits might be that question mark that we were seeing earlier. Maybe the next 16 bits are color, and so we're going to paint these particular letters that we just pasted on our screen. We're going to paint them a color or a sound. And so the bits are coming into the processor one at a time. The processor has to be running at incredibly fast speeds in order for me to be typing my 100-page English paper and to have all of those bits moving into the processor. And we know that modern an AMD Ryzen 7 processor has 8 cores with over 4.8 billion transistors on board, and it is running at 3.7 gigahertz. That's 3.7 billion times a second. The bits are being passed into the processor. There's a bit, there's a bit, there's a bit. Over 3.7 billion times per second. So our processors are running at lightning speed. That's why I can watch a Shrek and Donkey video. So this is how data is represented in a computer. Seriously, if you have not given your computer a hug, you need to go hug it right now, because the fact that it runs, and it runs as fast as it can, is an absolute Harry Potter miracle. The fact that I can type in my 100-page English paper, which by the way is due tomorrow, and then be able to print it out to turn in is an absolute miracle. So give your machine a hug.